Today we will do electric field. Now electric field due to a charge is the space around a charge in which any other charge experiences a force of attraction or repulsion. So for example, if we have a charge plus Q here, so this charge plus Q will develop an electric field around itself here in such a way that if we bring another, let us say charge, let us say a test charge plus Q naught, this test charge plus Q naught will experiences a force of attraction or repulsion because of the electric field which is produced by the charge Q, here. Okay, so the force of attraction or repulsion will be depending on the characteristic of these two charges. If both of them are positive or negative, that means if they are like charges, they will the force experienced by the charge Q naught will be repulsive, and if these two charges are unlike charges, so the force experienced by the test charge Q naught will be attractive. But we have to remember that this charge Q naught here will experiences a force because of the presence of the charge Q here at this point, let us say point O. So let us say plus Q naught will be at point P. So the charge plus Q naught which is at point P will experience a force because of the charge plus Q which is at point O. This is called the electric field which is set up by the charge plus Q. Now we know another topic. Let us go to the next topic, that is electric field intensity. Electric field intensity. So now after learning what is the electric field, that means the field which is developed by the charge around itself. So as a result of it, any other charge which is approaching it or come close to it will experience a force. So now let us see what is the electric field intensity means. The electric field intensity at any point in space is equal to the force per unit charge exerted on an extremely small positive test charge placed at that point. Now let us consider a point, let us say point charge plus Q here. Let us consider a point charge plus Q located at point O in space. Now the charge plus Q set up an electric field in the space surrounding it here. So because of this charge plus Q here, we have an electric field in this region here around the charge. Now let us say if a small positive test charge plus Q naught is placed at point P, so we already know that the charge plus Q naught will experiences a force. Let us say the force will be F, experiences of force F. So here both of them are positive, so the force will be repulsive. So F here. Okay, then we can see the electric field E. The electric field E at point P is given by E, which is equal to F by Q naught. So electric field intensity at any point in space means it is equal to the force per unit charge, okay, per unit charge, force per unit charge exerted on an extremely small positive test charge, okay, which is placed in the region near to the let us say charge, in this case the charge at O. So here the unit is Newton per Coulomb. So the electric field is given by the ratio between the force, that is force divided by the charge. Now the following points may be noted here. Number one, electric field is a vector quantity. So electric field is a vector quantity because F is a vector quantity, so naturally E also will be a vector quantity. So it has both magnitude and direction. Number two, the SI unit of electric field is number one, a vector quantity. Okay, so electric field is a vector quantity. Number two, the SI unit is Newton per Coulomb. Okay, the electric field, the SI unit of electric field is Newton per Coulomb. Also, sometimes we can write the unit of electric field as volt per meter, but we should remember that the SI unit is Newton per Coulomb. Number three, let us see number three, the dimensional formula of electric field is given by E, which is equal to F by Q. So we know that F will be equal to M1 L1 T to the power minus 2, and Q will be equal to A for current into time T. If we bring all this denominator into the numerator, we will get M to the power 1, L to the power 1, T to the power minus 3, and A to the power minus 1. So this is the dimensional formula of electric field. Now the electric field lines, okay, I'll explain what is the electric field line. So we already know the electric field and the electric field intensity. Now because electric field cannot be seen, so in general when we write it in paper, we used to represent it by lines, what we call electric field lines. So suppose if the charge is here, for example plus Q. Now let us say this is a charge plus Q. So to represent the electric field which is coming from this charge, we represent it by some lines like this. Now these lines are called electric field lines. So again I repeat, the charge, the electric field coming from the charge is represented by lines, what we call electric field lines. Similarly here, if it is negative, then electric field will come from infinity and end up in the charge like this. So in both the case, these lines, what you have seen here, all these lines are called electric field lines. Now we will learn something about electric field lines. Electric field lines start from the positive charge and end at the negative charge. So we must remember always it will start from the positive charge here, plus Q, and it will end up in the negative charge minus Q. So it will start from here and end up there. Always like this. It will come from the positive charge and enter the negative charge. If there is a single charge, then they may start or end at infinity. So if there is only a single charge, like this case plus Q, and or like this case minus Q, then the electric field line will, in the case of positive charge like this, they will end up to infinity. They will continue this side, all the sides, they will continue till infinity. Now if the charge is negative, they will start from infinity and end up to the charge like this. See, they enter, all of them, they enter, end up at a charge minus Q. They start from infinity and end at a charge minus Q. Now in a charge-free region, the electric field lines can be taken to be a continuous curve without any breaks. So if it is a charge-free region, then the electric field lines will start, let us say, from a charge like that, then it will continue to infinity without any break. The two field lines can never cross each other. Okay, so we already know that electric field is a vector quantity. Now it is electric field lines is the representation of the electric field. Hence, you see, for example, let us take two electric field lines here. Two electric field lines. Let us say this one and this one. Just take the example, these two field lines. Let us say they are intersecting at point A. Now we know that these electric field lines are vector quantity. Now, for example, if we look at the electric field lines 1, then at point A it will have two directions. One is along X, another one is along Y, which is not possible in the case of a vector. The vector cannot have two directions at one point. Now, similarly, if we look at the electric field line number 2, at point A again, it will have two directions. One is along X, another one is along Y, which is again not possible for a vector quantity to have two directions at the same point, in this case at point A. So as a result of that, these two field lines cannot be intersecting each other. So they may go very close to each other, but the two electric field lines will never ever intersecting each other. Electrostatic field lines do not form any closed loops. They are always start from a positive charge and end up entering a negative charge. They will never form a closed loop. Okay, so they will start from a positive and end or entering the negative charge, like this. Start from here and end up here, but they will not form a closed loop. They will not come back like that. They will not form a closed loop like this. They will start from positive charge plus Q and end up in the negative charge minus Q. So with this, we complete the topic today. Thank you.